Thank you. Thanks to all the organizers for setting this very nice workshop at GGI in Florence. It has been great to interact with many of you over the past weeks. And indeed, today I would like to continue the discussion on the way we estimate quantities, parameters in physics, and the related issue that has been sometimes referred as the inevitable dependence on the prior. Okay, so why this arises essentially because we love Bayes. So to introduce this problem, let me here just present a very simple toy model. This is a two-parameter model with linear dependence and a quadratic coupling controlled by a small coupling constant alpha. Let me assume the truth is 0, and for simplicity, no noise, such that the data fiducial is also 0. And let's put a Gaussian prior on theta 0, such that the posterior is given as follows. So suppose we're interested in getting the value of theta 0. What we would do is to marginalize over the other parameter deemed nuisance by integrating out over all the possible value, the joint distribution. For this very simple model, this can be done exactly. And in the small alpha limit, I'm simply Taylor expanding. So now what we want to compute is actually the posterior mean estimator. Essentially by computing the first moments of the posterior distribution, and this can be done by introducing a Gaussian generating function. And by taking derivatives of g, I can compute the zeroth moment, the normalizing evidence, and the first moment, which is the mean estimator of our parameter of interest. And what we see is that the mean is biased, okay, by exactly a value which is proportional to the coupling constant alpha. So this is what we call prior volume effect. So if alpha is 0, then the truth is recovered. And this happens essentially in two situations that often we are in physics. The first one is in the large data limit. Essentially, this is the central limit theorem. When we have enough samples, distributions tend to Gaussians. And this means that the Fisher information is dominating over the non-Gaussian tails. And in unit of the Fisher, alpha goes to 0. The other situation is where alpha is 0 from the start, right? For a linear model. So in physics, when we study systems near equilibrium, we can linearize the equation of motion and sometimes find linear solutions. Okay. So in these two cases, we are very happy. Unfortunately, there's a lot of other cases, as we know, where we're not in this ideal situation, and this is what I want to touch upon in this talk. So I will divide my talk in two parts. First, I will give a brief historical account of the prior dependence. And in a second part, taking some inspiration from those early works, I will try to advocate for what happened? A way to systematically minimize the prior volume effects. Okay, so spoiler alert, this very issue of the prior dependence was at the center of spark debates between the initiator of the people that developed statistics. So our story starts with Pierre Laplace, who wrote a treatise on probabilities. And here are the rules that he enunciated on the left in a form close to the original one, and on the right, a more modern translation to a language that we used to. And as you can see, the way that probabilities were assigned back then was really almost exactly the same way we are doing it today, okay? Famously, Laplace would put bets, for example, for estimating the mass of Jupiter or Saturn. He would say that I would place a bet of 11,000 against 1 that the mass that I have estimated fall within 1% of the estimated value. And this is exactly one-to-one with the way, with our beloved 68% credible intervals. Okay, so if there was one aspect of his work that was the target of numerous critics was the principle of insufficient reason, which is the situation where we have no prior information, we assign equal probability weights to the possible events. Among the critics on this principle, here is one by George Boole. The principle of assigning to different state of things of which we know nothing, and upon the very ground that we know nothing, equals degrees of probability is an arbitrary method of procedure. And another strong critic of Laplace work was Fisher, who was actually developing what we now call the frequentist approach, the method of maximum likelihoods, that was calling this principle of insufficient reason a doctrine and saying essentially the same thing as George Boole, that this would reduce all probability to a subjective judgment. So this is typically the kind of examples Fisher and friends would present to make fun of a Laplace theory, which goes as follows. Take a flat prior, say, on a given parametrization theta, such that the posterior distribution is simply given by the likelihoods. Now, choose a reparametrization as you wish, and now put a flat prior on this new parametrization. Now, you see that the posterior is not only given by the likelihood, but it is also proportional to the Jacobian of the transformation. Okay, so in the limit where the data is strongly peaked, in the large data limit, this is fine, but this is not the limit that we're going to look at. Just to say that this was not merely a war between Frenchmen and English gentlemen. There was also some continental critics, and for example, I invite you to see the Bertrand paradox. Okay, so the next character of our story is Sir Harold Jeffreys, that when he was not busy solving problems in geophysics or astronomy, he was writing a book on the theory of probability in the very tradition of Bayes and Laplace. And what he had to say about the principle of its insufficient reason, he essentially enunciated this way. If we have no information relevant to the actual value of the parameter, the probability must be chosen so as to express the fact that we have none. Okay, so far so good. But from that, he deduced something slightly different than Laplace, which is his famous Jeffreys prior, by requiring parameter invariance. And the prior is enunciated as being proportional to the square root of the Fisher determinant. So a slightly better defined mathematically way of looking at this prior is to upgrade the flat Lebesgue measure to a curved measure in parameter space. And now, when we assign uniform probability, it's no more in Euclidean space, but on this resulting curved space. Okay, so how does this legacy is influencing modern cosmology? Well, as you know, we still have this problem of prior volume effects, and here are some examples. So some example from weak lensing, these are mock data that are fit by the kids collaboration or by the desk collaboration, and you can see that the posterior mean are substantially shifted with respect to the truth of the mock. And in comparison, the point estimate that we call the MAP, the maximum a posteriori statistic, is well recovering the truth, as this is not suffering from those prior volume effects. So for this very reason of prior volume effects, when results are quoted, often the posterior mean and the credible interval is shown together with the map, here shown in crossed. And we see for different combinations, sometimes some substantial shifts. As you know very well, yes, please. Right. So exactly. So this depends on what you're interested in. If you want to compare the consistency between, let's say, this data set and another data set under a certain model, then you would just compare the full posterior. So this is fine. This is well defined. However, this is well defined if you use the same measure to define the probability distribution when you do this comparison. However, if you now just want to compare one number, right, which is the number we usually quote in the abstract, here you probably want to do it in the most precise way that you can, right? So yes, because now there's some degeneracies between amongst the cosmological parameters and also the nuisance parameter that you marginalize, we end up with this situation. Right. So you can say, okay, so for example, H naught, maybe this is not the best way to compare, but it seems that this is what we do. But now suppose you want to claim for detection of a new physics, right? And the parameter controlling your new physics parameter, if it's 3 or 4 sigma, let's say 3 or 5 sigma, it changes a big deal. And if you have shifts of 2 sigma, which is generically something that you expect, if now you enlarge your parameter space, you expect to introduce parameter degeneracies. So the data is weak in this sense, and so therefore it is expected to also have some prior volume effect in this case. And so the question is, for typical detection, right, maybe this is good to solve. Of course, if your detection is 10 sigma, you're fine, right? Yes. Right. So I think this problem appears even when you want to compare the full cosmological posterior, because beside those you have, as you say, added nuisance parameter. So if you want to compare, let's say, the cosmology you get from an experiment to another one, you will have to marginalize over the respective nuisance that might give some prior volume, right? So to make this very precise, you should be able to control the marginalization coming from the other parameters, right? Yes. Yes. What do you mean by intersection? Like you need to define the way you intersect, right? So you will, but because when you say I intersect, it means that you choose a particular direction in this higher dimensional space, and you need to give the prescription on how you do that, right? And this is measure dependent. Yes. 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 I agree. Yes. No, I agree. I agree. Okay. I think I can go fast on all these examples, but this is my conclusion. It means that there's no ideal metric actually to create to build confidence or credence in our theory if we do it in a very naive way. So I think it is indeed a problem-dependent question. But for the case that we're interested in this workshop, which is galaxy clustering, there might be a way where we can have definite answer, at least for models where we do not introduce too much degeneracies, and I can comment on that. So this is the case that we know very well in galaxy clustering, where two groups having two equivalent parameterization of the EFT of LSS at one loop for the galaxy power spectrum fitting the same data, we're getting different results. And essentially, this was due to a different choice of prior on those equivalent parameterization, however, leading to different prior volume effects. You can see some significant shift. While, however, the MEP was agreeing. The same exact exercise was done in the context of the Z full shape for different prior choices, and also in the combined analysis with BEO, where there's significant shift between those two statistics for DESI alone on the W0 WA model. And correct me if I'm wrong, that was one of the reasons why the results for this model was not shown for DESI alone. So what have we tried to do to solve this issue? Well, some have tried to put some educated guess on a parameterization that minimizes the prior volume. Okay, and this is fine. So it seems that if we choose wisely a parameterization, we can minimize those effects. Some others has looked at frequentist metrics. So these are diagnoses of the BOSS and DESI full shape using those alternative profile likelihood construction with their respective confidence interval prescription. And we see some broad agreements. However, there's still some discrepancies with the posterior statistics. And this frequentist approaches has especially been used in the context of new physics. As I was saying, there we might be introducing large degeneracies. So these are examples for the neutrino masses, and this is also now a famous, let's say, almost canonical example of new physics. Early dark energy, where a new species is injected, which fraction is controlled here by F. And it is realized when then F goes to 0, the other parameters associated to this new physics, say the location of the peak, so the epoch at when early dark energy is injected, or the initial phase of the action, basically get unconstrained, right? So this gives rise to a lot of prior volume, and this is why some of those frequentist metric diagnosis has been applied for this type of problem. So this is where I want to go. To summarize this first part, in the large data limit, we all happy, okay? Distribution are Gaussians, priors are irrelevant, and everyone agrees. And the problem arises when we are away from this data because distribution are Gaussian, the prior may become relevant, and no one agrees, right? Okay. But at least can we do something for the case we're interested in here, galaxy clustering? And before looking directly at how this would look like, I would like first to develop the idea of how we can minimize prior volume effects based on what we have learned. Okay, so it seems that if we're clever enough to find a good parameterization that minimizes those effects, we're good. And we can also take inspiration from the Jeffrey measure that provide parameterization invariants. And so in this recent work that we have done with two good friends, Alex and Henry, we have found, let's say, a systematic procedure to find this optimal parameterization. And the answer is that you start from a given parameterization of your model, and the Jacobian of the transformation that brings you to this optimal parametrization is given by the Jeffreys measure. So said differently, we prove that under Jeffreys measure, the posterior mean is an unbiased estimator. This is done under some technical reason that I will detail, but this is the claim. So I will show two proofs, a short one and a long one. So this is the short one. Basically, you start by whitening the fissure. Say you can do a Koleski decomposition, such that now you can define an orthogonal basis, right? And what you find is that the Jacobian of this transformation is exactly the Jeffreys measure, such that really the Jeffreys measure is what brings you to this space where the measure appears locally flat and your parameters are orthogonal to each other. So you don't have any prior volume effects, right? In fact, we started not with this short proof, but we started with the rather dumb and calculate proof. And this is the one I want to show. Essentially, we get in the same results, but maybe this provides some further insights, okay? And I will comment on them next. So to introduce the long proof, let me first give some definitions. Those are standards ones. So I define the posterior mode as the global maximum. So this maximum a posteriori. And what I'm interested in is to compute the posterior mean, which is defined as the normalized first moment of the posterior distribution. And in fact, what I'm actually interested in is to compute the average of the posterior mean, okay, to average out the noise and look what is left. What is left is the bias of my mean estimator. So we'll proceed this proof for asymptotic normal distribution, which means that my distribution has a global maximum, the mode, and departing from the mode, distant regions decay exponentially. So said differently, asymptotic normal distribution in the large sample limit tend to a Gaussian which variance given by the inverse Fisher. And here I will assume no model misspecification, meaning that my data is generated by a process which is well described by my model, such that this Gaussian is centered on the truth, okay? So let me define a bit more precisely what is controlling this asymptotic series. Essentially, gathering more samples will be controlled by a parameter n, okay? So this is the number of samples I'm collecting. In cosmology, you can think it as the number of independent observed sky patches. And then you can look at the quantities of interest, how they scale with n. So the more data you collect, the more samples you collect, the more the data volume grows, and the more your error bars shrink, okay? And you can go on and so forth, and you find that the Fisher information grows with n, okay, as expected. So here, again, I will not be interested in the large sample limit, but rather I will look at n finite, right? So essentially, this will be just, for me, a bookkeeper for my asymptotic series of the posterior. So the sketch of the long proof is the following. Under the Jeffreys measure, I start assuming that the mode is unbiased for simplicity, technical reason, and I find that the mean is an unbiased estimator of the mode. Second step, I look again at the modes, and I find that it's a biased estimator of the truth. So I need now to revisit the mean. So by not assuming that the mode is biased, what I find is that there are actually extra contribution in the mean that exactly cancel the mode bias, such that the posterior mean is an unbiased estimator, okay, for the technical cases that I have explicited. At first order in the Laplace expansion for those asymptotic normal distribution. So recasting this in formula, what I'm interested in is to compute the distance of the mean to the truth, that I can write as the distance of the mean to the mode plus the distance of the mode to the truth. And I call the first term the mean to mode bias and the second term the mode bias. All right? And the mean to mode bias is essentially given by the mean to mode bias, assuming that the mode is unbiased, plus a difference that we find to exactly cancel the mode bias. Such that now my average posterior mean is simply given by this mean to mode bias, assuming unbiased mode. So this was remarkable for us because, as you see, this is something I can compute given the posterior data. From the posterior data, I can get the modes. And so then I can actually estimate this bias by expanding around the mode, as I will show. While the mode bias instead is computed around the nominal truth, which is in principle something that I don't have. So this was remarkable for us that there was such a cancellation, and it wasn't clear actually if there was a deeper reason. So this is an open question. Okay. So from there, let's redefine our expectation value with respect to the Jeffreys measure. And by doing so, we find that the posterior mean is unbiased under sample average. So I would just want to show a few details of this proof. So I will not show how to compute the mode bias, but ask me if you're interested, know how this extra contribution arises. But let me just show the computation of this term, okay? The average mean bias, assuming the mode is unbiased. So the way to proceed, remember the toy model I have introduced at the beginning, we're gonna do it in full analogy. So now my model is a general model of n-dimensional parameter vector theta that I can expand around the mode. To be more precise, I'm actually expanding the posterior with Laplace approximation around the mode and computing the resulting posterior moment. So this is written as a Gaussian part with some higher order corrections that depends on powers of delta, the distance to the mode. And the Laplace approximation of my posterior is can be fully written in terms of the Fisher and the source term. So again, I can define a Gaussian generating functional, okay? And by taking derivatives of this generating functional, I can actually compute posterior moments, okay, with this simple replacement rule for the powers of delta to the derivatives of g. By doing so, I find for the posterior mean a leading noise term, as it should, and a first order term that under sample average does not disappear for Lebesgue measure. Okay, so let me walk you through this step. The source term is proportional to the difference of the data minus the model evaluated on the mode, here the truth, such that when you take the average of delta, this null. So the source term average is 0, such that the noise term here is also 0, as it should. Now, the data has variance, right? Such that indeed this noise term is given by the inverse Fisher, as it should. And for the same reason, the bias term at first order is non-zero under Lebesgue measure. Now, I redefine my expectation with respect to the Jeffreys measure. Expanding this measure at first order, I find that the contribution of Jeffreys to my average posterior mean exactly cancel the bias under Lebesgue. Okay? So this is, in a sense, the proof. Yes. 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 This doesn't work indeed. Yes. This is, as you know, is an asymptotic series, and so it might diverge. Yes. So I don't have a definite answer, but I can give you a criterion to tell you a priori if this procedure will work. This is essentially given by the expansion parameter of this series that I can estimate. I haven't written it here, but I can estimate. And from numerical experiments, we find that if the expansion parameter of this series is less than 1/3 in terms of the variance, this usually works. Beyond, it simply doesn't work. So if it doesn't work, what happens in this situation is simply you get an answer which is as biased as before, right? Simply the series is not converging, but this is just not, anyway, that's the thing. Yet, that doesn't mean, as I will show you, that you can only correct for small biases, for the reason that biases from higher volume effects can accumulate. They scale actually by the number of parameters that you marginalize. So they're, in a sense, large N enhanced. So let me show you an example of now using this type of curved prescription on a realistic scenario in galaxy clustering. So this is a Daisy-Mock full shape analysis consisting in 7 skies. And for each sky, we fit it with a one-loop power spectrum model comprising 12 parameters, which give us a total of 84 nuisance parameters that we need to marginalize over. So first sanity check, I fit my mock data with tiny error bars. And in this case, the parameters are recovered very well. This is the shift in sigma with respect to the truth. This case is the red contour. Just a sanity check. Okay, now for Daisy realistic volume, if I use the standard flat Lebesgue measure, I find 1 to 2 sigma shift on my cosmological parameters, in particular here, the log AS amplitude. So you see, this is a very large shift. And as we have done the exercise, if now I keep the volume fixed and I change the number of parameters that I need to marginalize over, this thing basically is scaling with the number of marginalized parameters. So this is small epsilon that needs to be small for the series to be convergent, but they can accumulate. Okay, now the next things we do is to actually use the Jeffreys measure, but using only the first order correction that we have calculated. So for that, we get the blue contour, which is essentially just a shift of the gray one, simply because at first order, the Jeffreys measure is only touching the first moment of the distribution. Next, we use the full measure, and we find the yellow contour. And as you can see, the higher order corrections that we have not calculated in this measure are touching the higher moments of the posterior distribution, such as the variance or the skewness. You can see it by comparing the yellow with the blue. And you can see that at each step, the prior volume effects are decreasing, such that when we use the full measure for this example, we are basically under our usual thresholds in data analysis. The final case that we have studied is actually using an alternative, in principle superior measure that we have found than the Jeffreys one. However, up to a non-large N enhanced term. So in principle, this will just give a small correction. And this is indeed what we find, that the results are even better under 0.1 in sigma shift with respect to the truth. Okay, so this seems to work. I would just like to comment that these chains were run on the laptop in less than an hour with PyBird JAX, which is the latest upgrade of a theory code, PyBird, that computes predictions in the FT of LSS for LSS correlators. In this companion paper, we present this implementation, which is basically a JAX upgrade with some neural network emulation that are cosmology dependent, that brings the runtime to essentially 0.1 to 1 millisecond for computing one prediction. depending on if you're on CPU, GPU. And what is nice with these new AI technologies is that now we can essentially compute the derivatives for almost free using automatic differentiation that give us derivatives of machine precision, such that we're able to compute the Fisher in the Jeffreys measure at each point of the MCMC with minimal extra costs. Okay, so here are my conclusions. We have found that under Jeffreys measure, the posterior mean is an unbiased estimator at first order in Laplace. Now, if you're not a fan of non-flat measure, you can really think of Jeffreys as the Jacobian that brings you to the parametrization that minimize prior volume effects. Okay. And I would just like to add that, as we have shown with nowadays technologies, getting Fisher on the fly at each MCMC samples is computationally tractable. So the question I'm asking is there any reason left to not use Jeffreys? And before finishing, I would like to put our results in the context of past work. So after all, our proof is just simply a Laplace expansion of a multivariate asymptotic normal distribution and the computation of the resulting posterior moments. So this seems to be rather straightforward to do. And it seems, and I say it seems, that our results agree with past calculation, although for us it was rather difficult to make sense of all those past work, since it seems that there exists a wide variety of notations in the literature of statistics. But if there are any two differences, here they are. We are consistently treating the noise on the sample average, tracking both the bias in the mean and the mode. And we're really focusing on the posterior moments, although we just did the really first step. There is another line of research that goes by the name of probability matching prior, where the focus is on posterior quantiles. And there is a rather strong results, which if you require the posterior quantiles to have the same coverage properties as the frequentist analog, you will find that the matching is only possible at first order in Laplace. And guess what? It's again the Jeffreys. So this leaves us with some open question, especially since we have seen on numerical experiment that the full measure is superior than the first order correction that we have calculated. And this is true for all the numerical experiments that we did. Yet it would be good to have, let's say, some kind of mathematical evidence that using this full measure always plays in favor in minimizing those prior volume effects. And so the question I would ask is, at those high orders, is a certain matching possible for a certain truncated hierarchy of posterior moments? So as we have learned from posterior quantiles can't be matched at higher orders, but maybe if we lower our criteria, maybe this is possible. And I'm saying this because it seems to me that what we care in the end when quoting a number, a credible interval, is just the first few moments, a mean, some variance, and maybe some asymmetry. So I stop here. Thank you. Okay, first of all, we start with the question. Is the statement here that map is always unbiased, or in this application? Yes. Here we're in the situation where essentially we, if you want, matching the posterior mean to the map up to the bias that we have calculated. However, it seems that this bias in the mode is small because it's not large and enhanced. So it can only be as large as the parameter controlling this expansion. So up to this small correction, yes, we in the situation. Exactly, exactly. Yes, you ultimately, if you're in this situation where the map would be biased, you need to go back to simulated data, right? Where you check these kind of things. But here I really assume where we not in the ideal world of Gaussians, but sufficiently close, right? I fully agree. In these more general situations, I do not have an answer. What we have done here is really just a small step out of the ideal world. And for this very crazy distribution, I do not have an answer. Yeah. Right. That's the usual objection that I hear. It seems to me that it depends on what you want to do, right? If your goal is just to quote a number in the abstract, right, to just have an estimation of the physical quantities you're after, you can do this. But however, when you want to compare two experiments together, usually you just go the long way, the full posterior comparison, and you do not look at marginalized quantities, right? Um, so I don't think these two things are incompatible. What here I'm saying is that the Jeffrey is just a prescription for computing marginal quantities. While when we compare experiments, if possible, we would try to do it not on marginal quantities. Yes. Yes. Absolutely. 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 If we have enough theoretical data, let's put it this way, that could solve this problem, this would be great, right? However, it's a bit unclear to me if for large scale structure, we will ever be in this ideal situation. Because essentially in this program, we're always introducing a lot of EFT parameters, especially when you crank up the tower of endpoints, right? So there's in principle always some signal to noise ratio to gain. And by doing, but if you want to do it in a controlled way, you introduce more and more nuisance parameters. Say you're interested just in the BO, right? And say we forget a moment how to do reconstruction, you would just naively do it by cranking up the tower of endpoints. So you're just interested in this signal, but to fit the broadband, you're always introducing more and more nuisance parameter, right? But this doesn't mean that, so the overall signal to noise ratio might not, once you marginalize over this theoretical noise, might not grow, but for the particular feature you're interested in, it will, right? Or say, for example, non-Gaussianities. So it seems that for some specific science case, such as those ones, it's possible that we just have too much theoretical noise, maybe, for this specific problem we're interested in here. Yeah.
Is that a similar thing as your split group where you
Yes.
And so you're essentially just finding the shape of the parameters which is going to be the best if you go to the basis where
Yes. 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 So even if they're unconstrained, the fact that they're simply now orthogonal to all the other parameters, once you marginalize over them, it doesn't matter, right? And yeah. No. So what I'm saying is simply instead of sampling B1, you sample some combination of B1 with, let's say, sigma 8 and complicated combination, which the transformation is just simply given by this. Then at the end, you're still looking at the posterior of AS, right, or sigma 8. You're not looking at the posterior of those complicated combination. I'm not sure if I was answering the question. Yeah. Yes. So yes, I mean, if I say it more simply, you see when DESI samples sigma 8 B1, and I don't know, they still look at just the posterior of sigma 8, right? In the sense, you can always look at the posterior of derived parameters. So, yes. Right. Uh, maybe you're right. Yes, I trust you, Stephen, on that. Yeah, for sure.
Okay, so it's also this is looking on non. If I just diagonalize,
Yes.
I would only get linear combination. This does also show non.
So that's the question. Yeah, that's for me not super clear. Yes, it's not super clear how to proceed at higher orders. It seems to me with this very naive argument, it's not clear how to proceed further. But with just the computational way, in principle, we could see. I mean, this type of proof essentially apply. You can do it for any posterior moment, right? And check what is the bias. So like, let's say the most naive way I would proceed is just compute the bias in each estimator. And what you can define as your new estimator is essentially your old estimator minus the bias you have calculated, right? And you can do this for the mean at higher order. You can do it for the variance. You can do it for the skewness and so on and so forth, right? I'm taking if you mean the expectation, I'm taking the sample average. Yes, I'm doing that. Yes. So the Fisher here, right, is parameter dependent. So it's not depending on the data, right? Sorry, the way I'm defining the Fisher is this way, if you prefer. It's not the average of the Hessian of the likelihood. It's not exactly. It's not the true Fisher information. This is just right. Right. This is just yes. This is just an overloading of the name of Fisher. Yes. Not the real Fisher. Yes. Now, because indeed, here, what I'm not showing the proof is that I was always saying up to small corrections, but if now you take some sample average, you do find something which is not totally described by the Jeffreys, which is some asymmetric derivatives of the Fisher, but this in principle is small. So I just eluded it for simplicity. Yeah. Yeah.
I guess that on the test that should would be something. I don't know exactly. Process also method to swap for sure. But since they're all degenerate, they're always okay.
Yes.
Well, all these factorial elements where the
Yes. Yeah. The hope is that by going to this diagonalized basis, those irrelevant parameters, since they're orthogonal, does not contribute anymore, right?
I'm pretty sure that the first side is relevant. Put all the one prior and cats. Yeah, because like I said, if you have something that's pictures telling you it's gonna train it at 1,000. But if you put a prior two on it, like you would, but once you go up to that base, then you put a prior two on it. It will take the first two that actually the other ones will just put prior, but it's not gonna change your like constraint on the on that much. Like I don't know the goal is how you choose the prior. Prior still the same prior as the original case, or now it's not prior.
Yeah, that is a good question. I think so for as it comes for the FTLSS, what you want really to control is the size of the loop terms, not the bias in principle. We say the bias control the loops, so that's why if you do it in a very approximate way, you just put the prior on the biases. But the better way to actually approach this problem is to actually put the prior on the size of the loop themselves, right? So that everything stay within perturbative control, such that for any parameterization you choose, it should be in terms of size, in terms of bounds, the same exact prior. Yes. Yes. Super large Gaussian, as if they're flat. So for the exercise here, the prior doesn't matter, the one I showed. But, well, okay. I looked at the situation where my data was sufficiently constraining such that I didn't need to worry about the biases for this particular analysis, right? Now, if I would let's take DESI, not final DESI, but a little bit of less volume, everything goes south, right? And then, yes, the prior matters. I need to be clever. Right, so flat measure is an arbitrary parametrization of the EFT of LSS. And I'm putting a large flat prior 510 on that basis. Yeah, so my claim is that for Yes. In here, in principle, I have not addressed this question of the prior, right? Well, I can just leave them flat, right? For all parameters. So when I say flat, essentially it's flat everywhere.
In a worse example, here it's flat prior, and then just the measure.
Almost, let's say, because it's flat with some bounds. But so I claim that the prior is not totally non-informative, but you know, reasonably not, right? Yes. Yes. No, so what we have found is that if you use these better prior, but actually putting on the loop terms, this is actually a little bit more informative in the example we have with math than just doing the naive order one prior on the biases, right? So it seems that there's some information to gain if we do a proper implementation on that, and that for me would be the prior. And this prior is parametrization invariant up to prior volume effects that can be controlled, right? I think it depends on the data, right? So depends on the fiducial and so on. So yes, I think you're referring to this plot here, right? Not this one? Ah.
The question from the one, the new one. Yeah, because now he was coming out of the UA. I guess, I don't know how much of the original.
So you see, for my arbitrary parameter start with, I have 2 sigma almost for log AF. Some 1 sigma for WA, right?
So this looks like already that go beyond minus the n a little bit.
Yes. Yes. So yes, you still need to be in a region where you have enough data, because if you have not enough, this will not work. I can tell you. Yes. Yeah. So the way you quantify the prior volume is depending on the measure you assign to parameter space. So yes, you can see it this way if you want. Yes. Yeah. Yeah, it's the volume measure of your space, right? So it gives you the metric to move in this space in the way that now know the curvature, right? So exactly. So when you do a parallel transport in parameter space, I mean, if we build on this analogy, you just do it in straight line now, right? So that's really why it looks orthogonal once you know this metric, which is given by the Fisher. Yes. Uh, I don't think so. Here, I think, yes, as you say, you may consider this is not an important problem, right? It's just that I was hearing too much of those around, and I was trying just to figure out what was going on. Yes, for actually getting a proper Bayesian evidence, I think we have tools, right, to work on the full posterior. I mean, the usual metric is the delta chi-square, fine, but you can do it in a much proper way. And ultimately, if you want to say claim detection of something, this is what you would go for, right? And nowadays, with the computer we have, there's absolutely no problem in computing the Bayesian evidence, at least for these simple analysis. So yes. Yeah, I would say we need to be pragmatic here, right? I mean, the first thing you do is just a delta chi-square. If it's small, I mean, you don't worry being very accurate in computing a better measure of your evidence. I think you start being accurate in computing an accurate measure when you're very close to a detection threshold, or in principle now the data volume is large enough so that it should be quite under control, or those effects you're telling you should be hopefully small enough so that you get a definite answer, right? This is but this is, yeah, this is just opinions. Sure, okay. Okay, but okay. No, but yeah, I agree. This is a true question because for some parameters, it's unclear what is the threshold. Yes, yes. This is actually a good question. Yeah. With and without this? Ah. With and without supernovae? Yes. Mm. Okay, so yes. It seems to me that if you constrain a direction very well, such that in this direction there's no tail, it's very well constrained. This is whatever the prior measure prescription you're going to have, this is not going to move. So if there is, you know, in the space of the that DESI constrain this particular direction given by supernovae, whatever the measure prescription I'm using, I think this is going to be not moving, right? So yes. Ah, for DESI one, I'm not sure that this will work if you don't put any supernovae, because I think that there the data is just too weak. Though one needs to check, right? Because for when you have so much nuisance parameter, this can build up. So yes, it's just for report. Yes, it's just a reporting numbers, and I can give you. I mean, if you read the paper, I can give you a criteria to show when this strategy will give you a, in principle, better estimates, right? So you can a priori check if this is a good thing to do. If the series is not convergent because you're in too much in this asymptotic tail, then just don't. I mean, then I mean, probably the analysis is useless. That's just my point of view. I guess you specify a prescription on how you assign probabilities, right? And yes, it is this you need to specify it a priori. But if you believe this is a better way to do it by just because you see, the way we do it is by putting a uniform distribution on Euclidean space, but this is as arbitrary as this prescription. This is just what I'm saying. There's not, you can't say the way we do it now is superior than that in the sense that, you know, you just define how you assign probabilities and then you just do it, right? It's just like there is a standard way to do it, but it doesn't seem to be the most clever way, right? Yeah, but each time you change the parameterization, you change the prior as well. Right. Right. So when you put uniform prior on Euclidean with the flat measure, this is totally sure. If you want to require uniqueness of the prime measure, then this is probably better. But if you're happy to abandon the uniqueness of the prior, then I think there's some alternatives. Yeah. Yeah, it will be different. Yes, it will. Yes. It will be. Yes.
And then I take that new thing, and I also, I would guess that the parameters that are, I mean, the parameters that are totally unrelated to the others.
Yes. Well, it depends. So when you combine, you might define a new Jeffreys measure for the combined analysis. But right. But
Yes, the shift parameter is one, and it's supposed to kind of change the ones that are untrained, like the B5, B10, and that's not gonna come. No, because like, I mean, for example, the reason yeah, I wonder if it finds that one, but
so you could do a partial orthogonalization, right? This you can always do, and then you just left with the. You can define a unique prior for your cosmology. You leave them aside, and you block diagonalize only the nuance if you're happy with this solution. What I'm saying is that the uniqueness of the prior is unique only because we live in one realization of the universe. You go to a parallel universe, someone have worked out another parameterization of the model, and it will be another prior. So the uniqueness for me is something that is fake in that sense, right? It's unique just because it's convenient. It's simplified our way to define it once and for all. But I mean, since the way we choose the prior is arbitrary, I don't think uniqueness is a good criteria in that sense, right? So you go from one experiment to another, but in another experiment, I mean, yeah, right. That's my point, I think, or my position at least. Yes, yes. There could be some middle ways, or yeah, depends on your taste, I would say.
paper without the data set, this is probably giving you a better understanding of the number. If you combine the data, then you'll get one calculation. And obviously, the best way to do it is combine all data and analyze everything. Yes, that would clearly be the best way. And all your volumes are going to intersect in the right way. But you don't always do that. So it would be interesting to see how it might give exactly how it's looking. Is it mixing parameters? weird way, like it's,
So you always have the cross correlation between the common parameters, the cosmology, okay, between the two experiments. And so if now you want to really go for these kind of things, it will surely redefine the measure. I mean, the measure would be different if you now want to compute posterior marginals for the combined one, right? And but you could do it again in a block diagonal way, and maybe you it works sufficiently enough. Though again, if we really in this new physics business, maybe you're always at the very edge where your data can tell something, and so you need to really combine everything. And again, then what do you do in these cases? Yeah, yeah, yeah. Sure, sure. Adding data will help at some point if you don't introduce extra parameters. If this is what you mean? Yeah. Ah, I see. Yeah, 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 yeah. Yes, maybe yes. Yeah.
not well. This would change something. Like the formula, it will say rotation space. Now, if you add a bispectrum and it breaks the degeneracy, but I mean, the data breaks the degeneracy, so there's a strong information. Then when you compute this measure, it will change so that it's not weighting the current parameter much. So I guess adding in the other thing and then doing this measure will say, you will know that both combinations are now determined. So in the power spectrum, this measure will throw away undetermined combinations of parameters. But if you add in more data or more circles, it will not throw away both. I guess that's how it will work. No, I know, but I mean, it goes through the whole list and it finds, I mean, so the ones that are now in common, B1, B2, B5, they will break that together. And then it will do a new rotation for B7 and 10. Because those are going to be left. Just have one for. How do this onboard WMW thing that the nation
I don't know, this is 20%, no? For W naught. So yeah, LSS alone is so naively this is 100% and this is 10-ish%. So this is very, very low precision. Now we have like 2-3%, yeah, 5% maybe. Yeah, it's much. Sorry, yes, yeah. So I was just quoting W naught, but for WA, WA is a bit larger. Yes, it's also order 1. Right. Yeah, 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 indeed. No, yeah. Ah, yeah, indeed, yes. Just full shape. Yeah, no, without reconstruction.
Probably not. 0.2 to 0.02.
Yeah, I mean, I think you break a lot of degeneracies in these cases, right? Yeah. There's too much degeneracies to make sense of the gain in error bar. Good one.